This is a good overview of the power rules. The first rule is the zero rule. Any base raised to a zero exponent is just 1. In symbols, we write a b, which is any base, raised to 0 is 1. This is true for numbers and symbols. Here are a couple examples. I encourage you to try to solve them. In each case, anything raised to the 0 power is 1. This one turned out to be -4 because the thing raised to the 0 is the parentheses and anything inside of them. It gets crossed out and left with just -4 times 1, -4. The one exponent rule states that anything raised to the first power is itself. This works the other way too. It also states that if you have a number or variable without an exponent, there's the invisible one. We call this the invisible one rule. Given 5x raised 1, I'm just left with itself, 5x. Now, what are the exponents of the 5 and what are the exponents of the x? Well, there's nothing written here, so I could write an invisible 1. There's nothing written here, so I could write the invisible 1. Now, what if I have a bunch of different bases and exponents? Well, I look for the ones with the same bases. Example, in these symbols, I have both bases being x. Those are the big ones. The small ones, the exponents are different. What I'm going to do, the rule says, is add the exponents. So since they're both x's, I keep x, and I add the exponents n plus m. Pause now and try these examples. I have both x's, so I add the exponents. I keep the base, I get 9. I have both x's here. Using this rule, I should have an invisible 1 that I see here, and I have x to the 4 y squared. Different bases, I do not combine them. In this one, I have a 5 and a 5 make 25. X to the 4 and nothing to combine it with. Y, invisible 1, with y squared make y to the 3rd. Try this one with numbers only. Same rules still apply. I look for the same bases. The 3 and the 3 are the same bases. I keep the 3, and I get 2 and 3 make 5. I don't have any extra 4s. I don't have any extra 5s. So this would be my answer here. Way too big numbers to ask you to even expand these. Now, oftentimes we're going to see a fraction with some of my bases on top, some of my bases on bottom. The rule is to subtract the exponents. The answer either goes on top or bottom of the fraction, wherever there were more. So I want to remind you of something. If I were to simplify the fraction 5 over 10, I would say, oh, okay, I'm going to divide by 5 on both. And my answer is 2, right? 10 divided by 5 is 2. But since there's a bigger number on bottom, my answer of 2 goes on the bottom. My answer is actually 1/2. So we're going to do the same thing. When I have the same bases, x and x, I'm going to look at the exponents, subtract them in either order, and the answer either goes on bottom if the bottom one was bigger, or on top if the top one was bigger. Let's see a few examples. Pause now and try these. In both of these, in this case I have x and x, I have 9 and 4. I'm going to subtract 9 minus 4 is 5. So then it helps me to see a fraction bar. And I'm going to put the x on top of the fraction because that's where the more x's were. And I have 5. Now in this case, I have 5 and 5 as my base, not a variable anymore, but a number. But they're the same is the important piece. And in this case, I have 10 and 12. Well, 12 minus 10 is 2. And I have more on bottom, so I'm going to put a 5 on bottom, squared, 1 as a placeholder. And this is a small enough number where I would ask you to simplify as 1 over 25. The negative rule, sometimes called the reciprocal rule, states move the negative exponent to the other side of the fraction bar and then make the exponent negative. In symbols, if I have x raised negative n, it's a positive n on bottom, or if it's x raised negative n on bottom, it becomes x raised positive n on top. Try these 3 examples. In the first example, I need to see a fraction bar, because anytime I see a negative exponent, I need to see a fraction. So in the first one, they didn't give me a fraction. I need to show a fraction. It started on top like a whole number. It goes on bottom now with a positive exponent. There's nothing else to do here except put the 1 placeholder. In this case, I still need to see a fraction so I understand top versus bottom. This is y -6 on bottom. It becomes y +6 on top. And actually nothing. I can put a 1 placeholder on the bottom, but there's no fraction anymore, so that's actually just my full answer. Here, there's a few things going on here. I'm going to put a fraction bar so that I can see the top versus bottom. I have a -1 exponent on my x, so it goes to the bottom as a +1 exponent. My y is -3, so it becomes +3 on bottom. And my z to the 4, nothing to do there, so it's just z to the 4. And again, these are all on the bottom, nothing on top, so I need my +1 placeholder on top. This last rule is called the power to power rule, and it's expressed like this. I have a single base, and I have 2 exponents. You see that 1 exponent is attached to the base, 1 exponent comes after parentheses. And very simply put, you need to multiply the exponents. Let's see a few examples. Pause now and try these examples. In the first one, I have a base of 2, and then 2 exponents attached to them. So I'm going to need to multiply these, 2 to the +24. This is way too high of an exponent. I'm not going to ask you to expand that. In this case, I have an x base raised to the 5th, raised to the 3rd. I need to multiply the exponents. I got x to the 15th. In this one, I have a couple of things being raised to the 4th. So I need to see the different exponents here. In order to multiply them, I need to notice that, oh, this x has an invisible 1. I'll say that again. I have a base without an exponent. I have a 1 exponent rule at the top of my paper that says if there's nothing there, there's an invisible 1. So if you see a big base without an exponent, put the invisible 1. Now I can say 1 times 4 is x to the 4th. I could say y to the 2 times 4 is y to the 8th.